Welcome back to Discovering Geometry with Mrs. Berry. This is lesson 33. In this lesson, we will look at the properties of parallelograms. There's actually 4 properties that we'll look at today. And then at the end, we will look at what vectors are and how we use them in physics. Remember that a parallelogram is a quadrilateral, 4 sides, whose opposite sides are parallel. We'll discover some special properties of parallelograms in this lesson. Where do rectangles, rhombuses, and squares fall? Well, all of them are parallelograms. Remember, a rectangle, 4 sides. And even though there's 90 degrees for a rectangle, these opposite sides are parallel. A rhombus would be all 4 sides being equal, whether it's a perfect square or whether it is a squished square, we still have the opposite sides that are parallel. Any conjectures we make about parallelograms in this lesson will also apply to these special shapes. But for our discoveries, we don't want to use a special parallelogram in our investigations because we want to make sure that the conjecture applies to any parallelogram. So as you draw your first parallelogram, make sure that it is not a square, rectangle, or rhombus. So our first investigation, we're going to split into 4 parts because there's 4 properties for us to look at. So for all 4 parts, we're going to need a little piece of graph paper, patty paper, or just a compass, a straight edge, a protractor, and a pencil to write with. So using the lines on a piece of graph paper as your guide, you're going to draw a pair of parallel lines that are at least 6 centimeters apart. Then we're going to use the parallel edges of your straight edge to make a parallelogram. We're going to label it LOVE. Then we're going to look at the opposite angles. We're going to use our protractor to measure the angles of the parallelogram. And we're going to compare the opposite angles using patty paper or our protractor. Here's what that should look like. Here's a piece of graph paper, and I'm drawing on the graph paper on the lines so that I have parallel lines. I'm then using both sides of my ruler to draw the other parallel lines. And you can see that's not a rhombus, it's not a rectangle. I then use my protractor to measure these angles. I'm just using my ruler to help me get a line all the way to the edge of my protractor. Now, when you compare those opposite angles, what do you see? The parallelogram opposite angles conjecture. Hopefully you found in your parallelogram that the opposite angles of the parallelogram were congruent. You see on mine that I had a pair of 76 degrees and I had a pair that were 104 degrees. And why does this work? Why does it? Why are the opposite sides, the opposite angles, congruent? Well, if we think about this being a parallel line to this one, and then just use one of these as a transversal, we should get that corresponding angles are congruent. So these would be congruent. And then up here, also 2 parallel lines. These would be congruent. So these original 2 parallel lines that we use for both of these, and then because the transversals are parallel lines, we could switch, and so these would also be congruent with the ones down here. So in our setup, all four corners are going to have corresponding angles congruent. And it also means that their vertical angles would be congruent. And so now when you look at it, you can see that these would be congruent. Also means that these other ones would be, these little ones would be congruent as well. So all four corners, because of the two sets of parallel lines, all four of these corners are going to have the same four corresponding angles that are congruent. And the ones opposite, so again, this one with 2 and this one with 2, these are vertical angles, so we know that they're always congruent. So we really only have 2 measures in this entire parallelogram, 2 different angle measures. So now the 2 angles that share a common side in a polygon are consecutive angles. So we're going to look at our parallelogram, and if you labeled it like I did, you had it as LOVE. So LOV, this one, and then EVO, this one, are consecutive angles. They're next to each other. So the consecutive angles of a parallelogram are also related. What did you notice as we were describing those angles? I want you to find the sum of each pair of consecutive angles. So you're going to find the sum of these two, find the sum of these two, and these two. So you're going to do 4 sums in your parallelogram. And then we will complete our conjecture. So again, I'm taking that same parallelogram that I have already used. I had measured all my angles, so it was very easy for me to find my sum. 76 and 104 every time. Every time I look at a pair of consecutive angles, I have both a 76 measure and a 104 measure. And that adds up to 180. You can see then that consecutive angles in a parallelogram are supplementary. They add up to 180. And again, if we draw out how we had said that all of these are the same set of angles, so all of these are corresponding, then that makes sense, because if this one and this one are the same as these two, and then we have this one here and this one, we can see that we only have 2 sets of angles. Well, if we measure the 2 angles here, they're on the same line. So of course they add up to 180. If we just transfer this one over to this one, then these two would be 180. So part 3 of our investigation. How are those 2 conjectures we just found out? How can we use that to find all the angles of a parallelogram if we're only given one? So let's think about that really quick. If this was a very good parallelogram and drawn correctly, and I said that this one was 60, how would we know what other angles? Well, with our first conjecture, we know that the opposite is 60. And with our second conjecture, we know that these two are going to add up to 180. So if this is 60, this has to be 120. We also know that any other set of consecutive angles, whether this one or this one, would add to 180. So you can go from either direction, or you can even use the first conjecture again and say that the opposite ones are the same. So this one is 120. So with only one angle in a parallelogram, we know the rest of the interior angles. Now let's look at the sides. looking at the opposite sides of a parallelogram. Use your compass or a piece of patty paper and compare the lengths of the opposite sides. So here I'm just using my compass to compare. Once I set it for one, I compare the other, and I find that they're the same. So the opposite sides of a parallelogram are also congruent, just like the opposite angles were congruent. Now we have one last part of our investigation. We're going to look at the diagonals. So we need to draw in the diagonals LV and EO, and then we'll label the point where the two diagonals intersect as point M. Now we're going to measure just part of the half of the diagonal, so LM and VM. And what can we conclude about point M? Is this conclusion also true for the other diagonal? And how do the diagonals relate to each other? So here I'm drawing in my diagonal, and the point where it intersects is point M. Now I'm measuring mine. You see that my first diagonal, I got about 4 centimeters on either side of M. My second one, about 3.5. So that shows me that my diagonals are not congruent. But my diagonals intersect in the middle of each of them. In other words, the diagonals bisect each other. So in a parallelogram, the diagonals of a parallelogram bisect each other. They'll divide both of those diagonals in half when you construct both of them in there. So those are our 4 parallelogram conjectures. And remember, they will also apply to rectangles, squares, and rhombuses because all of those are also parallelograms. Now, the last thing I want to talk about is vectors. Parallelograms are used in vector diagrams, which have a lot of applications in science, especially physics. So what is a vector? Well, it's a line, or really we'll use it as an arrow, but it tells us a quantity that both has magnitude and direction. In other words, a lot of times we might talk about our speed as we're driving a car, but that doesn't tell us what direction we're going. If we change that to saying, what's our velocity is going to tell us how fast we're going, our speed, and what direction we're going. So velocity would be a vector. It's a quantity that has both a magnitude, a number associated with it, an amount, how big or how little, and a direction. So vectors describe quantities in physics like velocity, acceleration, or force. There's others out there, but those are the main ones that we look at it for. And we can represent a vector with an arrow. When we use an arrow, the length or how long the arrow is representing its magnitude. Obviously, we can't draw it 100 feet per hour, but we can draw it relative. If you have 100 feet per hour in one direction and you have 50 feet per hour in one direction, you're going to draw them relative to each other. This one would be the 100, this one would be the 50. It's half as long. So the length represents the magnitude, and the direction of the arrow will represent the direction of the vector. In this case, both of these would be in the same direction. Maybe it's 2 cars on a racetrack, so they're headed in the same direction. Here's a picture of an airplane. In this example, the arrow is representing the airplane's engine thrust, this long arrow. And it's saying that the engine is giving the plane a velocity of 560 miles per hour in this direction. Hopefully you build your airplane correctly and it's flying it straight. We also have the wind velocity here. The wind is blowing rather large at 80 miles an hour. It's blowing not in the same direction that the engine is taking the plane. It is proportional to the plane's thrust in length. right? The 560 is much longer than the 80. Now, if we want to figure out where this plane is going, we have to combine these. The wind is affecting the plane just as the engine is. So in many physics problems, we're going to combine vector quantities acting on the same object. In this case, the wind current and the engine thrust vectors determine the overall velocity of the airplane and where it's going. So the resultant vector is a single vector that has the same effect. In other words, we're adding the two vectors that are affecting this airplane together and getting a resultant. We also sometimes call it the vector sum because we are adding two vectors together. So the resultant vector is a single vector that would have the same effect as the two combined. Let's look at how we do that and where those parallelograms come in. So to find the resultant vector, we make a parallelogram with the vectors as the sides. We know that the opposite sides are congruent and they should be at the same angle. So we have the wind velocity down here and we have the engine velocity going across. And so this one up here would also be the same magnitude and direction as the wind velocity. We just draw some dots up here to show where that would be. And then we also draw the engine velocity over here, and that forms a parallelogram. So the diagonal of that parallelogram is the resultant vector. The resultant vector represents the actual speed and direction of the plane. So even though the plane is trying to fly in this direction, it's really going to be blown off the direction that it's traveling just a little bit. So if you were the pilot and you felt this wind coming from this direction, you would turn your plane just a little bit off so that you can head in the direction you really want it. The resultant vector shows the wind will speed up the airplane slightly, but also blow it off just a little. But you can see that red one makes it go, it's a little bit longer than that blue vector. So with the wind, you're going to be given a little bit of extra speed.